Hello, my name is Yazid Hasan, a PhD student at the University of New Mexico, and first author on this paper, and I'm here to present to you our work on defensive escort teams via multi-agent deep reinforcement learning. This work was motivated by situations with movement in crowded areas like airports or convention floors, where navigation becomes difficult due to the sheer number of people moving around and the unpredictability of their movement. In these problems, some robots can be used to protect you and make it easier to find your way. We can even think of current events and say that you can have the robots maintain social distancing of people. This problem can extend to bigger tasks like vehicular motion, where smaller vehicles can make it easier and safer for a cart or caravan to move by influencing the other cars. It also has military applications in keeping convoys or important payloads safe, and making sure pedestrian or civilian obstacles are not blocking their paths. So the problem at hand is as follows. We have an environment that contains a payload, which is the solid circle in orange, that is navigating the environment towards a goal. And we want to keep it safe. The circle surrounding it is the cordon area, which we want to keep clear. The obstacles, or the gray dots, move about the environment using social forces, which mimic pedestrian crowd movement, and it becomes hard to predict with a high number of obstacles. They choose a direction and try to move towards it, and the obstacles or escorts in their fields of vision exert a social force on them to change their direction. We have escorts in the blue dots that protect the payload and have LiDAR of 512 rays with 3 channels to observe escort, payloads, and obstacles. The range of the LiDAR is shown in the big blue circles. As such, the range of observation is limited and only provides positional information, and the agents do not have full knowledge of the dynamics of the entities. The escorts influence the obstacles by exerting the social force on them to change their direction, in turn protecting the payload. Now, for safety, we are concerned with breach events, B, where the obstacles enter the cordon area, and collision events, C, where entities collide with the payload. The goal of the task is to make sure the payload reaches its goal safety, which requires a policy to minimize the probability of events B and C from happening. Now, in our paper, we discuss and review several methods that work and works related to the topic, but the most relevant escort-based methods can be categorized as follows. The first category is passive protection schemes, where escorts maintain visual surveillance of the payload or surround the payload to keep it safe. There are many motion planning or control methods to maintain the formation, like potential fields used here, surrounding the payload, is effective with enough escorts as to completely cover the payload, and surveillance methods provide guarantees on coverage. However, these methods often deal with static or no obstacles at all, require offline planning, or require full observation and knowledge of environments. Second category is methods of active protection. Algorithms using differential games or geometric methods are used to assign interception tasks, and escorts try to intercept the obstacles. These methods provide optimal policies for protection in environments with aggressive obstacles that move directly towards the payload. However, they require full knowledge of the obstacles within range and deal only with fewer obstacles that have first-order dynamics, non-self-interacting obstacles. The most relevant methods to what we end up doing are learning-based solutions, some of which are learned extensions of analytical methods. These escorts protect a VIP payload moving in an environment, protecting it from different obstacle types. However, they do not consider dense environments or obstacles moving with complex interacting dynamics. For example, having preset waypoints, as seen here in the light gray dots, and require explicit communication channels for the escorts. These methods are all effective in their own right. However, our environment has more obstacles than any of them consider, an order of magnitude greater. Furthermore, the obstacles in our environment have complex interacting dynamics that these methods aren't designed to consider. We also have no explicit communication channel or full observations on the environment. As such, we propose an end-to-end deep RL solution. It's meant to deal with dense, complex obstacle environments and relies only on range-limited positional observations. Now, our solution is a reinforcement learning solution. So in reinforcement learning, an agent takes actions in an environment and it gets feedback in the form of a reward and a new state. This trial and error approach reinforces desired behavior based on the reward function we design. We assign a reward function reward to reaching the goal and surviving, and we assign a penalty to collisions and cordon breaches. Every state will have a value to indicate how good or bad it is. This can be represented by the Bellman equation, or an estimated expected cumulative reward for being in that state. The policy is then to take actions that maximize the value. However, this gets difficult when you have a continuous action space like we do in our problem. As such, we train the model using an actor-critic method, where there are two networks. The critic learns how to estimate the value function. The actor learns the policy, which is observing the environment and proposing an action, and it gets the feedback from the critic itself. The agents train individually in the environment too, so we have several agents exploring. While they could have their own individual policies, for the sake of scaling training multiple escorts, they all have the same policy. They're all training the same policy. So they end up capable of cooperating without explicit communication since they share the same model. And each episode also has a different number of escorts for reusability and speeding up the training, and makes our method scalable to varying number of escorts. Now, here we take a look at the architecture of our network. The input of the network is the observations collected by the LiDAR in the form of 3-channel 512 values. We stack the last 3 time frames in order to infer temporal information like speed and acceleration. It is then fed to alternating layers of convolution and max pool layers, ending in a dense layer. The output is a distribution over the vertical and horizontal velocities, which we sample to get the action. The learning maps observations at a location to the value of being there. We can use the state value estimation given by the critic in order to estimate the value of all positions in order to see where an agent would prefer to be. This is done by positioning a third escort at each position corresponding to a pixel, to obtain this mapping of preferred or high value positions and not preferred or low value positions. Red areas are areas of lower value, and blue areas are areas of higher value. We show the values sampled in a 10 by 10 square area around the payload, so the X and Y axes are positioned about the payload at the center. The circle in the center would be the payload, and the white circle around it is the cordon area. The smaller black circles are the obstacles, and the white dots are the escorts. Now we can see some emergent behavior and decisions that they learn without being explicitly told to. For example, the agents learn the shape of the cordon area without being given the radius or any other dimensions. Agents also learn to stay close to the payload and to follow it as it moves. They also learn to spread out around the payload according to the other defenders. They also learn the motion dynamics of the obstacles, like how they behave when pushed back by a defender. You can see being in this area yields a low value since it pushes the obstacle into the cordon with no escort there to protect it. To show the efficacy of our method, we compare it against other methods found in related works, such as static escort formations, protecting the payload, and spinning escorts rotating around the payload at maximum speed. Additionally, we compare it to a method which is optimal in an environment with first-order dynamic obstacles and lower obstacle-to-escort ratio. And we applied it to our environment, which has a complex interacting obstacles and higher obstacle-to-escort ratio. This method assigns obstacles to escorts based on geometrically determining reach and using maximum matching. This geometric method outperforms the static and spinning escorts and is therefore the most significant comparison. And here's a comparison of our method. So this is our deep reinforcement learning method, and you can see the agents learn how to spread around the payload and to follow it. We quantitatively show the difference in performance by plotting the success rates on the y-axis against an increasing amount of obstacles in the environment, the x-axis. We can see our deep RL solution in black provides an enhancement in safety over the baseline geometric method in orange, with equivalent numbers of escorts, and how it performs as the number of obstacles increases. These values are averaged over 100 episodes. This shows our method is an effective solution and an improvement to existing solutions. Another result that we wanted to explore is robustness. Reinforcement learning is susceptible to changes in the environment, as unseen situations are often hard to account for during training. So we subject our method to changes in the environment, from payload geometry changes, observation noise, or fluctuation in motion dynamics of obstacles, as seen here. We add fluctuation to the velocity of the obstacles, sampled from a normal distribution of different standard deviations. This makes the obstacle movements much more difficult to predict, and our method is not trained for random movement. We can observe how escorts perform in this situation. Here, we have the quantitative results of these experiments. We compare the ratio of success against the performance of having no noise at all, the y-axis, with an increasing in standard deviation of the social force fluctuation, the x-axis. As expected, the performance deteriorates as randomness increases. But the performance of our method is over 90% as successful as baseline, even at the standard deviation of 2. This, along with other experiments in our paper, show the robustness of our method to unforeseen examples. We also wanted to showcase our method's learned behavior as well as dynamic changes in the resources. Towards this end, we ran an experiment where the number of escorts changes during an episode. As we can see here, the episode starts with 4 escorts, and then they lose an escort and gain it back. They manage to arrange themselves accordingly around the payload. To see this result quantitatively, we plot the cordon breach reward, or a measure of the amount of cordon breaching that happens during the episode, on the y-axis. We plot the reward throughout the episode's lifetime, which is 400 time steps along the x-axis. The black line shows episodes where there are 4 escorts all the way through, and the blue line shows episodes where there are 3 escorts all the way through. The red line reflects the type of episode shown in the video, where the dip in performance coincides with losing an escort. We can see that despite the loss of performance in that period, it is still comparable to the performance of having 3 escorts all along. This is also true as the escort returns into the red line, jumps back up to the performance of the black line. The agents never see such episodes during training where the number of escorts changes during an episode. This shows our method is capable of dynamically adjusting to losses or gains in agents. So, in conclusion, we present a deep RL solution to the problem of protecting a payload using escorting agents. Our method provides enhanced safety over other current solutions compared against static and spinning escorts and against analytical methods as shown. Our method is robust to several changes in the environment like observation noise, motion dynamic noise, changing payload geometry, and losing or gaining agents. Our method also relies only on range-limited observations based on the position of other entities, in this case using LiDAR, with no explicit communication between the escorts and they cooperate using positional observations of each other. For future work, we're thinking about expanded environments with different conditions and variables in them, with different types of obstacles, and collaborating our method with other motion planning algorithms that might drive the other agents, might drive the obstacles, or might drive the payload itself. So thank you very much for listening, and we hope you have a wonderful day.